brute force at work. A European Ariane 5 rocket lifts off from Kourou. For Bepi Colombo, Europe's first mission to Mercury, the real journey has begun. Its 7.5-year flight is a major challenge in orbital mechanics and will see it reach the smallest and innermost planet in our solar system in 2025. There, its discovery mission will really begin. A joint program with the Japanese space agency JAXA, Bepi Colombo is one of the most complex scientific missions ever launched. It carries 2 orbiters designed to unravel many of Mercury's mysteries. These include an unusual magnetic field, strange surface features called hollows, and ancient ice hidden in polar craters.
One spacecraft is provided by ESA, which is MPO, we call it MPO, Mercury Planetary Orbiter. And this spacecraft has a focus more on the planet. We want to observe the planet, do remote sensing, characterize the surface, count the craters, wanting to know about the composition of the surface, the interior of that planet. And in addition, we have a second spacecraft, and this spacecraft is called the Mercury Magnetospheric Orbiter, more focused on the environment, and this spacecraft is provided by the Japanese Space Agency.
We know the Mercury is very hot, and we have to make the satellite that can survive in that harsh environment. And we know, well, it is very difficult, and when we started, we already some development, and we think that we can do it. But actually, the hurdle is much harder than we expected, and takes a long time. But now, you see, this is the flight model.
Bepi Colombo's road, design, research and development phase, the construction, assembly and testing phase, has been long and hard, culminating in the launch from the European spaceport in French Guiana.
Mercury is 3 times closer to the Sun, and therefore the radiation or the heat which we are getting from Mercury is 10 times higher. So everything which we had to develop had to withstand the higher temperatures, but also the higher radiation doses which we got from the solar wind. And for that we need special insulation of our spacecraft, special materials to be developed for the antenna, for the solar panels. And that was a very big challenge for the mission in itself.
Now, of course, we do the health checks to verify the system is healthy. And we did alignment, mechanical checks, electrical checks all over. We checked the propulsion subsystems to see if the propulsion elements are still leak tight in preparation for the fueling.
Hardware apart, training of the scientists and technicians back on Earth was extensive, requiring years of preparation.
Campaign is the first time that all the experts involved in the Bepi Colombo spacecraft design, integration, testing and operations work together as a single team. The campaign is essential for this group to learn to work as a single team, to train the decision-making process. The campaign is also very important for us to fine-tune our plans and procedures. It's the first time that we exercise the flight plans and procedures in a realistic context, taking taking into account communication constraints, ground station, and timing.
In preparing for a mission like this, we have to carefully train all the aspects. What we actually do in the rehearsal, we do in preparation of a launch, we train the teams to work together, we train the teams to work with the flight procedures, and also we train the teams as much as we can in flight conditions. So normally when we test before, we test with many workarounds. What we try to simulate here is actually to replicate as much as possible flight condition. And we typically do between 20 and 30 of these rehearsals before a flight.
With the nail-biting launch sequence complete, for many it's time to sit back and wait.
The cruise will be a bit above 7 years. We will fly by once the Earth, 2 times Venus, and 6 times Mercury itself, before we come into the orbit, which allows us to capture with the small gravity of planet Mercury against the big sun. That means when we fly, we constantly brake against the sun because we fly into the inner side of our solar system. Yeah, and when you fly towards the most heaviest element there, you constantly accelerate. We don't want that. That's why we decelerate.
Because this planet is so close to the sun, you need to have a lot of energy to go there. It's even easier to send a spacecraft to Pluto than to Mercury. You have to brake until the gravity of the sun, and you need a lot of energy. And for that reason, our mission takes quite a long time, because we also need the help of planetary flybys in order to bring our spacecraft there. Then we want to send 2 spacecraft in an orbit around Mercury, and that in itself is also a problem, because on the other hand you need to brake against the sun, but on the other hand you also need to accelerate your spacecraft to bring it in the same speed as Mercury goes around the sun, and then to finally drop it into an orbit of the planet. I'm working now 14 years on this mission, so it's really like a baby growing up and then leaving the house finally. So for me, it's a special moment.
Bepi Colombo's main component parts are 2 orbiters and 1 transfer module. These took 4 weeks to disassemble and pack, and required 70 shipping containers and 4 cargo planes to ensure safe delivery to the European spaceport at Kourou. Spacecraft have got up close and personal with Mercury twice before, thanks to NASA's Mariner 10 probe and, some 40 years later, the Messenger mission. Messenger mapped the surface and identified strong evidence for water ice in shaded craters. But its mission also raised new questions about this mysterious planet. This latest probe has a sophisticated suite of sensors and instruments that will come into play when it reaches orbit around Mercury.
So the big step forward for Bepi Colombo is the fact that we have 2 spacecraft, the European Space Agency spacecraft, which is looking directly designed to look at the surface of the planet and to study the planet in detail. And the orbit is designed such that you maximise the objectives that you can do relating to the surface, and the second spacecraft is designed to look at the environment. And so having 2 spacecraft will enable us to do a great deal of new science compared to the previous missions.
Bepi Colombo, with a 2-satellite approach. We have 1 satellite, the MMO, sitting in the solar wind, and the other one is inside the magnetosphere, so we can see what is coming towards the magnetosphere and what is driving changes within the magnetosphere.
We have 11 instruments on board the spacecraft, and when we are at Mercury, these instruments are gathering data, and then they will store it in effectively a large hard drive, which we have on board the spacecraft. That data is then collected over a number of hours, and when we have a visibility with the spacecraft in Mercury, typically it's every 16 hours we can talk to the spacecraft at Mercury. The data is then downlinked using a very large high-gain antenna. It's a very powerful antenna in order to have a data rate of about 340 kilobits per second. If you compare it to your home internet, this is nothing. It's a very slow data rate, but it's very fast considering we are very close to the sun and we might get some interference from the energy from the sun. So it's as powerful as we can have with the resources we have on board the spacecraft.
With the assistance of gravity flybys, the spacecraft will rely on its solar electric propulsion system. It consists of 4 TX ion thrusters, fueled with xenon gas that is ionized and electrically propelled out, providing thrust for months at a time. The thrusters will rely on the spacecraft's solar arrays for power. The T6 thrusters can accelerate Bepi Colombo 15 times more efficiently than a conventional chemical thruster.
The solar flux is 1.4, more or less 1.4 kilowatts per square meter. As we approach Mercury, which is the innermost planet of the solar system, that solar flux has risen 10 times. So now we have 14 kilowatts per square meter. Now you might think that's a good thing in the sense that it gives you more energy to turn into electricity to be able to run your thrusters. But it turns out that that immense flux that we're getting from the sun also drives the temperature of the spacecraft very high. And in particular, our solar arrays, which are sensitive to high temperature, need to be protected. Now, we do that in a number of different ways. We keep as much of the open surface covered in little mirrors that we call OSRs, optical surface reflectors, or with specially developed white coatings, which help to reject the heat from the sun. But perhaps the biggest mechanism that we use to keep the solar array cool is to off-point. Rather than pointing the solar rays directly to the sun, we point them at a very shallow angle. And what that does is it means it keeps the thermal energies under control while still giving us the necessary energy to turn into electric power for the thrusters. Now, the reason why the solar rays are so big is because we're off-pointing by so much that in order to get a sufficient cross-section of the solar array needs to be bigger.
Protected by multi-layered insulation, hand-stitched thermal blankets and a radiator to dissipate heat, ESA's Mercury planetary orbiter will have to cope with extreme environments.
If a unit is getting too hot, if one of the payloads is getting too hot, in order to stop that payload from being damaged, we'll switch it off. We'll send an emergency message back to the Earth, reporting that there's an issue. We need ESOP to take action to investigate why items are getting too hot, and then to recover the unit and the spacecraft.
Once they reach Mercury in late 2025, the orbiters will separate from the transfer module to begin their comprehensive scientific mission in 2026.
In principle, all the planets have the same chemical elements because the whole solar system has the same chemical composition, but it's distributed differently in different planets and different environments. So it's vital to understand what is the ratio of the abundances of different elements to understand the structure of the surface of Mercury.
One of the advanced sensors aboard Bepi Colombo is a sensitive imaging X-ray spectrometer called MIX, which produces a global map of Mercury's surface atomic composition at high spatial resolution.
MIX instrument, the Mercury Imaging X-ray Spectrometer, looks at the fluorescence that happens when the sun shines on Mercury in X-rays. So it's a bit like when you wear a shirt in party lights which has been washed in the right sort of washing powder. The party lights shine on your shirt glows. And it's exactly the same with the sun and Mercury. The sun shines on the surface in X-rays, and the surface of Mercury glows in X-rays. And if you detect those X-rays, you can tell what Mercury is made of. And what it tells you, you're actually counting the atoms on the surface. So it tells you in a very quantitative way exactly what the surface layer of Mercury is made of.
So I would say one of the most exciting things about MIX is the fact that we will be able to produce the first images in X-ray wavelengths of Mercury's surface. And that is going to be able to give us a great deal of new information, both on a global scale and on a local scale, of how the composition of Mercury varies over its entirety of its surface. Another aspect of the MIX science, which I'm personally very excited about, is the fact that we can also see X-rays from the surface which are being produced by particles from Mercury's magnetosphere actually precipitating onto the surface and producing X-rays that we will be able to also measure. So we can have an extra aspect to the science that we can do relating to how Mercury's magnetosphere interacts with the surface.
Among the mysteries revealed by MESSENGER are irregularly shaped depressions known as hollows, found in clusters over a wide range of latitudes and longitudes. These hollows have bright interiors and halos with a fresh appearance that suggests they are geologically very young.
I think that there are two mystery or two very intriguing objectives of Bepi Colombo. The first one are the hollows. The hollows are features discovered by MESSENGER. These features seems to be quite distributed all over the surface of Mercury, and is something related to the volatile that come to the surface after an impact, after a volcanic event. But of course we need Bepi Colombo to really characterize and to understand which is the origin of the hollows.
There are also clear traces of much more recent hollows where the surface has been eaten away by some process that removed solid volatile substances, such as sulfur, chlorine, sodium and potassium, as vapor.
And this is because we don't have the composition data. We can measure the dimension, the size of the hollows, we can have an idea of the distribution, but no more. And also, of course, MESSENGER didn't get so many high-resolution images, and didn't have the digital terrain model, the 3D images at high resolution, as we will provide with Symbiosis. In other words, I think that the hollows are one of the most interesting discoveries made by MESSENGER.
Existing evidence indicates that if combined and spread out over a city the size of, say, Washington, the amount of water ice concealed in Mercury's polar craters would be over 2 miles thick.
And the second point is the water, because even MESSENGER said, yes, on the polar region we may have some water ice, hidden just in the shadow of the craters, because in the polar region there are some floor of the craters, some wall of the craters that are always in shadow, as occur on the moon. But the messenger didn't have the instrument to observe if it is, to make a direct measurement of water, as occurred on the moon. And Bepi-Colombo and Symbiosis will be able to do it with our spectrograph.
If confirmed by Bepi-Colombo, the story of how the inner planets, including Earth, acquired water and some of the chemical building blocks for life becomes much clearer. It would support the theory that organic compounds as well as water were delivered from the outer solar system to the inner planets and may have led to prebiotic chemical synthesis and, as a consequence, life on Earth.
So studying Mercury is crucial to better understand the formation of our solar system, how Earth is formed and evolved, and where we are coming from. So Mercury is in a way a missing piece in the big puzzle of the formation of the solar system and a crucial end member because it's close to the Sun, and if you want to get this full picture you have to look at the planet close to the Sun, as we also did in past missions that we were looking at the comets or planets further out.
We all have our individual science objectives for each of our instruments, and what we're starting to do now is to bring all of our ideas together, which obviously are complementary to each other, and we can start to form a broader set of goals at working group level, so the surface working group and the environment working group, and that helps us to again maximise the science that we can get from the mission by coordinating what it is that we want to do, potentially looking at specific targets on the surface and that kind of thing. We can work together to get the best from the mission that we possibly can.
ESA science and engineering teams have already been working on Bepi-Colombo for more than a decade. But with a long journey ahead of it, the recent launch marks only the beginning of the next intriguing stage of Bepi-Colombo's voyage of discovery.